All right, hi chemistry students. Here's a little video for you guys on 11.3 redox reactions. If you're watching this on Tuesday, May 14th, you will know that I'm not here. I'm at the district office, and so you guys are doing this alone. So hopefully this video will help you guys be able to understand redox reactions a little bit better. I also really thought the POGL activity, the activity that you guys did in groups, is really good, and so that hopefully helped you guys understand most of it. But hey, this is a good way of putting everything together and hopefully clarifying some of those thoughts for you guys. And so let's first start off by looking at a redox reaction to understand what we're talking about. And so here's an example of a redox reaction. We've seen this before. We actually worked a lot with this before, right? If we have methane with oxygen, it forms CO2 and H2O. And some of you guys recognize that this is actually what we've been calling it so far as a combustion reaction. And it is indeed a combustion reaction. We do have some CHO molecule with oxygen making CO2 and H2O. And so, yeah, it is combustion. And in fact, yeah, it's going to make a flame. But it also is a redox reaction. We see in chemistry oftentimes there's overlap, and here's one example. So this is a redox reaction, and the reason why it's called a redox reaction is because this word redox means reduced and oxidized. And so we call it redox for short, but in a reaction where you have something being reduced and something being oxidized, we call it a redox reaction. So you might be saying, what are those terms? Well, here's the thing. You see here how we have oxygen, right? So because we have oxygen and it's combining with the carbon here in CH4, we say that carbon here is getting oxidized. It's getting oxygen added onto it. Whereas here, this oxygen, so some of them are going to go through this carbon, but otherwise some of them are going to get hydrogens, and so we say that this oxygen is getting reduced. And so the ancients, they saw that there was a lot of examples of moments where oxygen would combine with other things to make it something else, and so they made this idea of oxidation reactions where if basically something gets oxygen on it, it's like, oh, that's it's being oxidized. That is a good, starting definition, but actually it turns out that it's more complex than that. Even if you don't have oxygen, you can have an oxidation reduction reaction. And so let's define these terms for you guys. What is a redox reaction? And a redox reaction is a reaction in which you have one atom being oxidized, one being reduced. And what that means is that one atom is losing electrons and another atom is gaining electrons. All right, and so here's the definitions. If something's getting oxidized, it's losing electrons. If something's being reduced, it's gaining electrons. And so here, what we're saying is that the carbon here is losing electrons, and whereas, one of the oxygens here, they are gaining electrons. Now, how the heck can you tell that by looking at this? Or just looking at this chemical reaction? Well, you can't right now, and so we're going to learn some stuff so that you can understand what the heck is actually going on here. But yes, at the moment, you don't understand it. Now, one thing to note, you do need to have this memorized. This is super important to memorize these two definitions. That oxidization is losing electrons, reducing is gaining, oxidation is losing electrons, reducing is gaining electrons. There's a number of mnemonic devices that you can use, but here's how I remember it. I remember it Leo, Ger, and what that means is losing electrons is oxidation, gaining electrons, gaining electrons is reduction. Okay, so losing electrons equals oxidation, and then here gaining electrons is reduction. Okay, so you can remember it that way. So that's what a redox reaction is, that's what being oxidized means, that's what being reduced means. Well, now let's try to understand what the heck is going on here. So first thing you need to be able to understand what's going on here is you need to be able to determine oxidation numbers. And what oxidation numbers are, they're basically kind of like mini charges of sorts for an atom in a molecule. Now, so far this year we've been talking about gaining, losing, sharing electrons, and that's all true. And as I've mentioned to you guys many times in the past, these are building blocks, simple ways of explaining things to you guys so that you guys will understand it and you can understand other things in chemistry, but they aren't the full picture. It turns out that it's actually a little bit more complex than that the mini charge of an atom in a molecule can actually vary a lot, even depending upon the molecule that it's in. And so, how do we determine those mini charges? Oxidation numbers are. And so best understood via an example. So let's say we have P4O8. And so what are the mini charges here? Well, there are some rules for understanding this. The first rule is that O is almost always going to be -2. I said things can vary, but O, it doesn't really vary. O is almost always -2. There are some exceptions, we'll get to those, but for the most part, O is almost always -2, and in this case, it is -2. And so here, O has a -2 charge. Do note, though, that there are 8 of them, and so overall, this oxygen here is kind of making like -16 charge. Now, overall, this has 0 charge, right? We're not seeing any -1, -2, or +1 or +2 here, right? And so overall, this must be equal to 0. And so here, we must have +16 from the P4. Now, do note, if you were to take a look at the periodic table, you would think that the charge of P should be +3. But it's not going to be here because we have 4 of it. 4 times something has to equal to +16, +4. So P here has a +4 charge, which is different than what we would expect. Its oxidation number, we say, is +4. O's oxidation is negative. Oxidation number is -2. And so that's how you determine oxidation numbers, or that's at least one example. As I mentioned, again, there are some rules. I'm going to hopefully try to introduce them to you via some examples, because I think that's how you best learn. I don't want you to have to just memorize rules. Though I'll put it for you at the end, because well, memorization can be helpful too. But hopefully, hey, learn from some examples. So here we have SO4 - 2. What's the oxidation numbers? Well, O is, as we mentioned, almost always -2. And so this -2, there's 4 of them, and so this is overall -8. Now do note, we have a -2 here, and so everything here needs to equal to -2. So we need to have here, if this is going to be equal to -2, this is +6. +6, -8, we'll get -2. So that's good. Now S, there's only 1 of them. And so how can we get +6? What times 1 equals +6? It's going to be +6. So the oxidation number of S here is +6. And O is still -2. Again, you see that this is very different than what we would expect for sulfur. Sulfur, because it's in group 16, we would think is going to be +2, but it's actually +6. And so this is the interesting thing about oxidation numbers. They vary widely from what we expected. All right, let's take a look at another one, actually a couple here, which will really drive home for you this idea that oxidation numbers, especially for atoms, can switch. So I'm going to give you NO and 2O, and then NO2. All right, so take a look at the N in each of these situations. So in this first one, O is -2, and there's only one of them, and so overall that's -2 here. Now do note we don't have a charge, and so we're gonna want to get +2 here. And so how do we get +2 if we only have one of them? Well, it's +2, right? So the oxidation number of N is +2, and for O it is -2. And so here we see the oxidation number for N differs from what we would think. We would think it's normally going to be -3, but actually it's not, right? It's going to be +2. Now let's take a look at this one. Again, we have just one oxygen, so it's going to be -2. And there's one of them, and so -2 overall. Now do note, again, we have 0 charge here, so we have 2 to get +2 here. So these cancel, we need +1, right? And so what's the oxidation number of N here? It's +1. Oh, still -2, right? But do you see how it's changing for nitrogen? Interesting. All right, now oxygen. Here, again, -2. There's 2 of them, so we have -4. And here, it's going to be 0 overall, and so we need a +4 here. And so we only have one of them, so the charge of N here is going to be +4. And so here is +4. And so we see how the oxidation number of N changes based on what it is. And this is key to redox reactions. Basically, we see that the oxidation number of N can switch. How does that happen? Well, N to go from +2 to +1, it would gain electrons, right? And thus be reduced. Gain electrons reduced. Here, if it goes from +1 to +4, it must have lost electrons, right? And therefore must have been oxidized, lose electron, oxidized, Leo, right? And so this is what's key to redox reactions. That's why we need to know these. Here we're being reduced. N is reduced, here N is oxidized. Now, I'm not showing you, though, the specific way that we go from NO to N2O and NO2. We need what we would call here a reducing agent that would combine with NO to make N reduced. Here we would need an oxidation agent that would oxidize N and cause it to be oxidized. The point is, this is why I'm teaching you this. I know it's kind of annoying, but oxidation numbers are key to understanding redox reactions. Trust me, there are some things, right, that I don't like either, like learning the scales on the piano, but you have to in order to be able to understand this. All right, so here are your rules, if you really must know. You can actually find even more rules online. There's like lists of 13 or so. Here's just 3 that I want you to know, and I think this will do the job for most situations. And then we can look at this as we do some problems, see if we want to add on anything. And feel free to add on your own if you find more. The rules, after all, are for you. So here are 3 rules that I basically introduced to you via these examples. O is almost always -2. The halides, right, these are the group 17s, are almost always -1, and charge is equal to the overall charge of the molecule. And so these 3 rules will help you be able to determine oxidation numbers, which will then help you be able to determine what's being reduced and oxidized in your practice problems. Now, I do know that I didn't go over these. You can do these now based on what I just went over, as well as this one. But these, well, I'm hoping the POGL will help you guys out with that. And also, apply this idea of oxidation numbers here. I might make another video later to help you guys out with that. But try your best on these, okay? Because it'll help you apply this idea. And hint, hint, I may, make sure that you guys understood it when I get back. So please do your best. Really do fill out this worksheet. And yeah, I'll help you guys out when I am back. So hope that helped. Oh, last thing actually, before we close, I wanted to say, why am I teaching you this? Why is this useful? Well, two reasons. For one, it's an AP Bio, and a lot of you guys are taking AP Bio. And so in AP Bio, you guys will learn, for example, and take a look at this reaction, right, with the Krebs cycle. And it's going to be important that you can identify, hey, what's being oxidized, what's being reduced. It's something in AP Bio. So you'll have a leg up if you learn this now. But second off, very cool. It's this is how batteries work. Batteries are just big redox reactions. And a lot of the developments and improvements in battery technology that we've had in the last couple of years, and why we see Teslas everywhere in Woodside nowadays, is because of this, because of redox reactions. And so, and it's a big sector in the future. It's continuously growing. Redox reactions and battery development are actually very important. And so, hopefully it gives you guys a little bit of flavor, it gives you some of the basics, so that whenever you go in the future, you'll be able to use this information. So hopefully that helps. Let me know if you have any questions.